Hi friends! So this week we are starting to talk about air pollution. We're really getting into stuff in my wheelhouse concerning the atmosphere and climate change and things like that. So hopefully getting more into this lecture style sort of video is helpful. But before we start talking about air pollution in general, we have to really start talking about the atmosphere. We've talked about some components, right? But it's a good reminder to recognize what the atmosphere is. And it's this super ultra thin layer that goes around our entire planet. And by ultra thin, I mean super thin in comparison to the size of our planet as a whole. The Earth's atmosphere extends about 10,000 kilometers from the surface of the Earth, but 98% of that mass is concentrated within the bottom 26 kilometers. And then below that, 50% of our atmospheric mass is contained within the bottom roughly 6 kilometers. That's also where most of our weather stays, like thunderstorms, clouds, most air pollution, etc. It stays within this lower layer. And we'll talk about why that is here in just a few moments. But before we get into the structure of the atmosphere, it's good to talk about the composition of the atmosphere. Perhaps you've learned about the composition of the atmosphere before. If so, recall what those gases and concentrations are. Don't worry, we're going to go through exactly what they are right about now. So our atmosphere is comprised almost entirely of nitrogen. 78% of our atmosphere is nitrogen, which is interesting. Perhaps contrary to popular belief, where maybe we think that oxygen is the #1 component. However, it is actually only 21% of our atmosphere. And then we have varying components of the atmosphere. However, nitrogen is relatively fixed. So argon is relatively fixed. So nitrogen's at about 78%, oxygen's at 21%, argon is at about 1-ish. And then these other components here are what we consider our greenhouse gases, and they have varying percentages from place to place, from time to time. And we'll talk a little bit about why that is and how that is throughout this chapter and sections. So now that we've reminded ourselves of what the composition of the atmosphere is, which, by the way, I gotta say, this figure here is a little bit outdated because carbon dioxide is most certainly no longer at 350 parts per million. We are now at over 415 parts per million on an overall average. So our textbooks need to adjust these numbers pretty soon, huh? But now let's have a look at the structure of the atmosphere. What does she look like as we go up the air column? So the atmosphere is divided into separate layers. The bottommost layer being the troposphere. Above that is the stratosphere. Remember, we've talked about the stratosphere before when we talked about this lovely little thing here called ozone. Then above the stratosphere is the mesosphere, and above that is the thermosphere. And not in this figure here, but there is also the exosphere and the magnetosphere. So things really extend super, super far, and they're all very important layers. But we're going to concentrate down here at the troposphere. But what I want you to notice here is how temperature behaves as we go up in the atmosphere. And this is on average, by the way. So our x-axis here is temperature. So through the troposphere, we see a really nice decrease in temperature. And then once we reach the tropopause and into the stratosphere, then we see an increase in temperature. And an increase in temperature is what we call an inversion. An inversion creates a super stable layer within the atmosphere. That's one of the reasons why thunderstorms stay in the troposphere. Temperature inversions can also occur lower in the atmosphere and lower in the troposphere, actually, and that can actually help trap pollution because, again, temperature inversion creates an insanely stable layer. And this is really common actually at night, because at night the land cools down much faster than the air above it. It's called, oh gosh, of course now I can't remember the term for it, but radiative cooling. There it is, radiative cooling. So the heat is leaving the actual surface of the planet, which is then heating the atmosphere directly above it, which would create a slight inversion here at the bottom of the troposphere, and then it would continue to decrease as it went up. But that's one of the reasons why maybe you've gotten up in the morning, driven across one of the bridges for work, and you've looked over and you can't see either San Francisco or San Jose or whatever, but it's a beautiful sunny morning. It's because there's pollution there that's been trapped overnight. And then it won't get mixed out until later in the afternoon when that inversion goes away. But why do we care about air? Who cares, right? Why is it so important? Well, we use oxygen for aerobic respiration, carbon dioxide for photosynthesis, and nitrogen is used by all living creatures, as we recall from all the cycles that we talked about in the previous week, right? And then the air also helps redistribute water to the hydraulic cycle. Air also moderates climate thanks to the greenhouse effect in the troposphere. If we didn't have our atmospheric composition the way it is, we would be very, very cold little humans. And air also blocks harmful UV radiation. We talked about that when we talked about ozone depletion in the stratosphere and the ozone hole that exists over Antarctica, right? That whole thing. And then, so that's air, right? That's all of the air in the atmosphere, all well and good. So then what's air pollution? Well, air pollution from your book is defined as contaminants from natural sources or human activities that can cause health of environmental problems. And we have two different types of pollution, one being primary pollutants. So these are released directly from both mobile sources, such as cars, trains, ships, etc., and stationary sources, such as industrial plants, buildings, things like that. Then we have secondary pollutants, and that's when primary pollutants react with each other or with other substances in the air to kind of break things down or just create different chemicals in the atmosphere, which can then be also considered a pollutant. So from your book, this is infographic 10.1 through 2. So this has a really nice illustration of the various primary pollutants as well as secondary pollutants. So we have our names, kind of some sizes of them. We'll talk about particulate matters and the sizes and why all of that matters later on. And if there's any exceeding of any of these standards, there are standards set, by the way, by the EPA, and if those standards are exceeded, then we would say that they are out of compliance. So what I like about this particular infograph is it shows where the troposphere is and where like the top of it is and where it goes into the stratosphere, and then also shows our prevailing winds. So we emit things into the atmosphere. They can go up into the stratosphere potentially. It takes a little while to go from the troposphere to the stratosphere because, again, that really, really stable layer keeps everything quite down into the troposphere. Regardless, those prevailing winds are westerly, so they go from west to east, and it causes travel of those various pollutants. And we're relatively familiar with that, right? Anyone remember Apocalypse Day from last fall, right? Where there were fires happening in Northern California. They got the smoke got transported higher into the atmosphere, and then all of that smoke was then transported down here to the Bay Area, and all the skies turned that really ominous orange red. It was definitely a blaze day, or oh gosh, of course I said the wrong one, but Apocalypse Day is what I like to call it. So within pollutants, we have what we call criteria pollutants. So the EPA has set National Ambient Air Quality Standards, NAAQS for 6 criteria pollutants. So they look at carbon monoxide, sulfur dioxide, nitrogen oxides. There's several. So there's NO2, NO3, I think NO4 as well. And just for funsies, we call it NOx because it can encapsulate all of those. There's tropospheric ozone, particulate matter, and lead. And we're going to explore parts of this website, but I wanted to pull this table from the EPA website, which again, as I said, you're going to explore later. But it shows primary standards for human health as well as secondary standards for public welfare. Primary standards are more so for the sensitive populations like children and the elderly, whereas the secondary standards are more for like plants, animals, crops, and buildings. I encourage you to explore this website and also take time to explore what this table is, what it means, and what it could potentially, what impacts it could potentially have. Next up, we have this table from your book, which is, I had it here, Infographic 5. So it highlights the criteria air pollutants, the various ones that I just mentioned. And what you should be able to do is list each pollutant, list a source, perhaps list an example, and any sort of environmental health effects. And I'll step through these just a little bit here. So carbon monoxide being the first one. So carbon monoxide comes from vehicles mainly. There's other things that it comes from as well, but it's very, very bad for human health. It is also, maybe you've heard, or maybe when the Texas cold snap happened back in February, I think, maybe you heard that some folks had died because they were trying to stay warm in their cars, which were encapsulated in their garage, and your car releases carbon monoxide. If you have too much carbon monoxide in your blood, then it can kill you. Sulfur dioxide is generally from natural sources, but also from fossil fuel combustion, like coal burning power plants. It can produce acid rain, things like that. NOx is from the reaction of nitrogen in fuel or air with oxygen at high temperatures. That can generally create smog, it can damage our lungs, and it can damage various plants. Ozone, we've talked about in the stratosphere, and that's really good in the stratosphere. We like it up there. But down here, not so much. And this is formed from reactions between NOx and VOCs in the presence of sunlight. And as I said, that can create smog. If anyone has spent any time in LA, you know what, you're very well aware of what smog is and what it looks like. It really leaves this nasty brown layer in the atmosphere. So you may have noticed that most sources from these 4 criteria air pollutants is that of cars, right? So what do we do? How do we help that? Well, we can make cars more efficient. We can drive more energy efficient cars, whether it be hybrid, electric, whatever. And that can help. And maybe you remember early on in lockdown, there were regions that had much better air quality because we were all stuck inside, right? We weren't driving our cars. Even places like India, villages in India could see the Himalayas for the first time in over 60 years because people were stuck inside and they weren't driving, they weren't releasing all this pollution. But other criteria air pollutants include particulate matter and lead. Lead, thankfully, has decreased in the atmosphere quite a bit, but particulate matter is of concern simply because of the size. So the smaller the particulate matter, the more concerning because it can go further into our lungs, causing more damage. And particulate matter can come from various farms, forest fires, dust storms, etc. Again, we should be relatively familiar with this one due to being in the forest fire space. But if you're not, then definitely familiarize yourself with this particular criteria air pollutant.